Hi everyone. So up until now we have been looking at covariant derivatives and Christoffel symbols, and we have seen that Christoffel symbols are a fundamental property of a chosen coordinate system, and we've seen a couple of different ways of finding Christoffel symbols in a certain coordinate system. So the first method I showed you, although we didn't really look at an example, we just stated it, but that was back in the first video for this chapter, and that was where the Christoffel symbols were defined as the expansion coefficients of the derivative of a basis vector. But then I showed you another formula where it can be found from the metric tensor, so without recourse to the basis vectors, and then we did an example of that in the 2D elliptic coordinates. And now we come today to the third and best and easiest way of finding Christoffel symbols in a given coordinate system, and it's by finding what are called the geodesics in the coordinate system. Okay, so finding the geodesics of our space in a certain system of coordinates. Now, what does that mean? What are geodesics? Well, if you imagine in my space, I have 2 points. Okay, so point A and point B. And I can connect these points by a path. Okay, so let's just call it C. So what's a geodesic, and what's it got to do with this? Put simply, a geodesic is the shortest path connecting points A and B. So a geodesic is the shortest path connecting 2 points. So, in this example, where here is point A and point B, my curve C is clearly not a geodesic. Okay? Because, as I expect you're thinking at the moment, surely the shortest path between 2 points is just a straight line. Isn't it? And the answer is yes, it is, if your space is Euclidean. Okay, now remember what that means way back from chapter 1. A space is called Euclidean if it's possible to use Cartesian coordinates. Okay, possible to use Cartesian coordinates. And it's non-Euclidean if it's not possible to use Cartesian coordinates. So for example, if you think, this light board that I'm writing on, okay, it's a flat piece of perspex, so that's a two-dimensional surface. Okay, you can think of this as a two-dimensional space, and A and B here are 2 points in that two-dimensional space, and it is a Euclidean space. Okay, you could draw Cartesian axes like that. There's X, there's Y. Yeah, this piece of perspex is flat. It's Euclidean, you can use Cartesian coordinates. So the geodesic between points A and B here, yes, it would just be that straight line, which I've drawn dotted. But if you imagine I have a non-Euclidean space, then the geodesic is not a straight line. Okay, there are no straight lines in a non-Euclidean space. And you might wonder, well, what exactly does a non-Euclidean space look like? Surely I can always use Cartesian coordinates in any problem. They may not always be the best choice, but surely I can always use them. I can always set them up. Well, actually, no. Okay, so if you imagine, for example, the surface of a sphere. Okay, so imagine, for example, the surface of the Earth. That's a two-dimensional surface. Okay, that's a two-dimensional space. Okay, so don't think of it as a three-dimensional sphere. Okay, so we're not thinking about the inside of the Earth, just the surface of the Earth only. Okay, so only on the surface. That's a two-dimensional space. Okay, so you can describe it with like two coordinates, which you can measure from the center. Okay, so like two angles, theta and phi. But it's just a two-dimensional surface, although it lives in like a higher three-dimensional space, okay? But that's how you can visualize it. So the two-dimensional surface is non-Euclidean, okay? Think about it. On the surface of the Earth, you can't draw a straight line. Okay, so if I said, you know, take my 2 points as being London and New York, what's the shortest path from London to New York? Staying in my space, so staying on the surface of the Earth. Well, it's not a straight line, because there are no straight lines on the surface of the Earth. Okay, you have to follow the curvature of the Earth. So in that case, the geodesic is something more complicated than a straight line. And that's in fact why, that's where the word geodesic comes from. So geo means earth, so it comes from the word geodesy, meaning like the study of the size of the earth and the shape of the earth. At any rate, what has this got to do with Christoffel symbols? How does this help us find Christoffel symbols? Well, let's think about how we would find geodesics in general. Okay, so if we've got 2 points A and B, and we want to minimize the distance between them, how can we do that? Well, let's write down how we actually calculate the distance along a general path C. So the distance along a general path C between A and B, what's that given by? Well, we just call the distance little s, and remember, it's the integral of ds along the curve. Okay, so it's just a line integral. And remember that ds is just the square root of gij dxi dxj. And typically we parameterize our curve. Okay, so if you have a general point on that curve, we specify its coordinates as a function of some parameter, which we can call u. So using the chain rule then, this complicated looking integral just becomes a familiar one-dimensional integral. So the integral from ua to ub of the square root of gij, and I'll write it like this, so x dot I, x dot j, du, where this dot just means differentiation with respect to u. So x dot I just means dxi by du. So that is how you calculate the distance along a general path C between A and B. Okay, so how do you find the shortest path? How do you find the geodesic? You want to take this integral, which gives you the length, and you want to minimize it. Okay, so we want to minimize the integral, and let me now just call it capital I for integral. This, okay, so ua to ub, I'll just write it again, gij x dot I, x dot j, du. Now, if you have done, or if you are doing at the moment, the calculus of variations module, then you might have an idea of how to do this. Okay, so this is a calculus of variations problem. Okay, you have an integral that you want to minimize, and I'm not going to go into the details of where this comes from. I'm just going to tell you the answer. The details are in the PDF lecture notes. If you're doing calculus of variations, you will already know this. But the answer is that the curve or path C that minimizes this integral, or at least makes it stationary, satisfies what's called the Euler-Lagrange equations. Okay, and what are they? They are as follows. d by du of the partial of L with respect to x dot k minus dl by dxk equals 0. Okay, we're here, k is a free index, so it can be k equals 1, 2, up to whatever the dimension of your space is, capital N. Okay, so in two-dimensional space, then there are really two equations here. So there's an equation for k equals 1 and an equation for k equals 2. In a three-dimensional space, there are three equations, and so on. And what's L, by the way? So I've just brought in this L. So L is whatever the integrand is here. Okay, so square root gij x dot I, x dot j. It's called L because it's called a Lagrangian. Okay, so it's called the Lagrangian function. At any rate, these equations, okay, which you will know very well if you do calculus of variations, or if you've done classical mechanics, you'll have seen them there. They're just called Lagrange's equations of motion in that context. These equations will give us the equations of the geodesic, okay, so the shortest distance between the points A and B. And how do we find this Lagrangian? So that's the only thing we need to know, okay? It comes from our whatever our coordinate system is, okay? So if you know the line element, so if you know like the expression for ds squared, then you can get the components of the metric tensor. Okay, now there is something that makes this slightly awkward, and it's this square root symbol, okay? So in general, when you have your coordinate system and you have your components of the metric tensor, then this Lagrangian with the square root, it's a little bit awkward, okay, because you have to take these derivatives in the Euler-Lagrange equations. So it turns out, and this is not completely trivial or as obvious as it might seem, but it turns out we can get the geodesics if we do the same thing, so use these Euler-Lagrange equations with this Lagrangian, but just forgetting the square root sign. Okay, so I'll just say here, but actually L equals Gij x dot I, x dot j will do. Okay, so what you're doing really there is, rather than minimizing the length of the path, you're actually minimizing the squared length. And it might seem like that's obvious. If I minimize the length, yeah, I minimize the squared length. That seems logical. It's not totally trivial, because something you have to bear in mind is that in what we're going to be looking at when we get into the relativity stuff, lengths can be negative. Okay, so yeah, remember in special relativity, you know, you have ds squared and it can be negative. Okay, so for particle motion you can have negative lengths. For photons you can have zero lengths. So this is not totally trivial, but we'll not prove it here. So I'm just going to say, actually, using this Lagrangian will do. And so what's this got to do with the Christoffel symbols? Okay, so that's what we're trying to do, get a method for finding the Christoffel symbols. Well, it turns out that, and I show the proof of this in the notes, I won't go into it here, but it turns out that if you take this Lagrangian and you put it into this set of equations, what you will end up with is the following. Okay, so these are then called the geodesic equations. Okay, so the answer really, okay, so the equations of the geodesics, it looks like this. So x double dot means differentiation with respect to u twice, superscript k plus gamma k I j x dot I x dot j equals 0. Okay, so the proof of that is in your lecture notes. Okay, so take this Lagrangian, fire it into the Euler-Lagrange equations, okay, which from knowledge of calculus of variations, they will give you the curve that minimizes this integral. Turns out, at the end of the day, this is what you get out if you do that. Okay, so you get this set of equations where again k is a free index here. Okay, so your geodesic curve, whatever it looks like, a general point on that geodesic curve has coordinates xi, okay, or xk, so x1, x2, up to xn, okay, and they are a function of u. And these equations here tell you exactly what those coordinates look like, okay, as functions of u. Okay, so these dots, remember, are differentiation with respect to u. And look, here are the Christoffel symbols, okay, so that's where they appear. So by finding the geodesics for the coordinate system and comparing the geodesic equations that we find with this general form, we can read off the Christoffel symbols. Now, I imagine that this doesn't make much sense yet, okay? So, as ever, the best way to illustrate this will be with an example, which is what I will do in the next video.